Okay, so if need be, you can refer back to our flow chart. First thing you got to ask yourself, is it polar or not? Then if it is, you need to clarify, is it one of these special ones that's nitrogen, oxygen, or fluorine with hydrogen? Okay. So today we're going to talk about, we're going to kind of wrap up talking about between groups. So like comparing something that has dispersion forces with something that has dipole-dipole. But then we're also going to talk about, what about if they both have dispersion forces? How can we differentiate the strength of their intermolecular forces then? Okay, so for the one we just started with, this one here, formaldehyde, that first one, has the oxygen in there, the double bond oxygen. So that's going to create the polar molecule. So it's trigonal planar, looks like this. Okay, but the oxygen's not the same as the hydrogens, whereas the ethane is nonpolar. So the difference in electronegativity between carbon and hydrogen, remember, is really small. So this is very important to save you a lot of time. Anytime it's just carbons and hydrogens, it's nonpolar. You don't need to like draw it out. You don't need to do anything more. If you just have the formula there and it's just carbons and hydrogens, nonpolar. Okay, which means that it is dispersion forces are the only intermolecular force present. Another tip is, if you've got carbons and hydrogens and an oxygen, then it's, at the very least, it's polar. It might be hydrogen bonding, but it's certainly polar. Okay, so we have the structure of this one. We can tell that the hydrogen's not bonded to the oxygen itself. And so this one is just polar, no hydrogen bonding, so it's dipole-dipole. Okay, so possible question types would be just, what's the dominant intermolecular force in formaldehyde? Or, indicate which has the stronger intermolecular force, formaldehyde or ethane. Or predict which has a higher boiling point, formaldehyde or ethane. Okay, in this case, we're basically saying, here's the trend, explain it. So it is virtually impossible to just measure the intermolecular force. It's not like we're not going to go measure that energy. The way we observe the strength of the intermolecular force is by things that we can easily observe, like melting point and boiling point. Melting point in particular is like something you can do. You'll do it if you take organic chemistry. You'll do it in that lab plenty of different times. You literally take this little tube, you put a solid in there, you stick it in a machine, and you sit there and watch it and wait for it to melt, and then you write down the temperature that it melts at. It's very straightforward. So when we look at those melting points, we can really easily identify which one has the stronger intermolecular force. So higher melting point, stronger intermolecular force, and that coordinates with what we see. Dipole-dipole is going to be stronger than dispersion. So that's why the formaldehyde has the higher melting points. And boiling point always follows the same trend. If the melting point's higher, the boiling point's going to be higher as well. The other thing to kind of notice here is that they have picked two molecules that have really similar masses. This is because dispersion forces are very affected by mass. So heavier molecules, we'll have a slide specifically talking about this in a minute, but heavier molecules will have stronger dispersion forces. So there is a range of dispersion forces depending on the molecule's size. So when we're comparing between two groups, like dispersion versus dipole-dipole, we need to make sure that they're relatively close in size. You wouldn't want to compare like a small dipole-dipole molecule like this one, formaldehyde, to like a really big, like octane, C18, H38, C8 rather. Okay, I was thinking of something even bigger than that. Let's say a big carbon compound, C18, something like that. Because it just wouldn't be a fair comparison, because one is going to have dispersion forces, but be really, really strong dispersion forces. Okay? So only change one thing at a time. That's mostly for me. I'm like reassuring you, I'm only going to change one thing at a time. Okay, take a look at the next one and see if you can identify why they have this trend in melting point and boiling point. Like, why is one higher than the other? Okay, so if we look at their boiling points, let's say, like I said, melting point's going to have the same trend. If we look at the boiling point, the ethanol obviously has a higher boiling point. So before we even identify what the intermolecular force is, we can say ethanol has stronger intermolecular forces, because it's telling us that it takes more energy to break those intermolecular forces apart. That's what boiling is. Breaking those intermolecular forces. Okay, so now let's identify why that might be. First of all, notice that they have actually the exact same mass. That's because they actually have the same number of carbons, hydrogens, and oxygens. These two are just isomers of each other, meaning that they have a different arrangement of how things are bonded. Okay? So in this case, on the bottom, you've got the oxygen stuck in the middle between the two carbons. The one above, they're kind of in a row, and the oxygen's on the end with a hydrogen. So they are trying to tell you what this looks like when they write it in this way. In fact, you'd probably more likely see it as C2H5OH, like that. And this one, you might see it written this way or this way. But when they write it with the OH on the end, they're trying to hint to you, by the way, it's an oxygen with a hydrogen stuck on the end there. Those are known as alcohol groups, that OH. And so that's a very important indicator when they write it like that, that it's hydrogen bonding, right? Because it has the oxygen with the hydrogen. So that's why this one, so H bonding, that's why this one has the higher boiling point, because it has hydrogen bonding, whereas this guy, it does have the oxygen in there. So like we said, it's got the oxygen. We know it's at least polar, but the oxygen isn't bound to a hydrogen. So this is just dipole-dipole. So that's why it's got the weaker intermolecular forces and therefore the lower boiling point. Okay, any clarifications about those before we move on to talking about within a group? Okay. All right. So take a minute and just look over this one. You're not going to necessarily know why it looks like this at this point, but just see what things you notice and how they correspond to the boiling point. So the first thing to identify is what type of intermolecular force is going on here. Well, technically it's not molecular because these are just atoms, but when we're talking about noble gases, they interact the same way that a nonpolar molecule would because it's just a single atom. So the way that they will form solids or liquids with their other atoms is through dispersion forces. Okay, so because they're completely nonpolar, they'll form dispersion forces in order to hold together. But just because they're all dispersion forces doesn't mean they all have the same boiling point, right? You can see as they get bigger, and by bigger, this could mean like we measure it by molar mass. That's usually the number that we'll give to like help you know that something is bigger. But really we're talking about the number of electrons, because the more electrons that it has, the more those can shift around and create bigger partial charges in the atom or the molecule. So with that ends up causing stronger dispersion forces. So they both have, all of them have dispersion forces, but xenon has stronger dispersion forces because it's larger and therefore a higher boiling point. Okay, so that's within dispersion forces. So there's another example of this down here. And I'm actually going to add to this a little bit. I don't know the exact boiling points, but somewhere in here we've also got methane and ethane. So these are all carbon-hydrogen compounds. So because of that, that means they're all dispersion forces. And on the x-axis, you've got the molar mass. So it's saying as the molar mass increases, the boiling point increases. So simply by like making observations like the one with the noble gases or like these compounds, we can identify that, okay, for some reason, I mean, we know why, but for some reason, as the molecule gets bigger, the boiling point is higher. Therefore, the intermolecular forces must be stronger. Okay, so all of these carbon-hydrogen compounds are the crud that comes out of the ground when you drill oil, okay? So there is a lot of different molecules that come out from crude oil. So there's everything from these really small ones like methane and ethane. So that's like the primary components of natural gas. And then there's the mid-range ones. So again, I said gas, natural gas. Those are gases at room temperature. There's the mid-range ones like octane. That's the primary component of gasoline. So those are liquids. When you start getting even more carbons, this is stuff like jet fuel is somewhere up in the 17 to 20-ish range. And that stuff is really like thick compared to liquid gasoline. Like it is not the same thing. And then if you go even bigger, this is all in the same stuff that gets pulled out of the earth. If you go to even bigger molecules, you get up to stuff that's like asphalt. Okay, which is a solid at room temperature, right? So even just looking at the states that they are at room temperature tells us about that strength. Because what we're saying is like the methane, the stuff down here, it's already bypassed its boiling point by the time you're at room temperature, right? You've already boiled it or evaporated it or whatever. It's turned into a gas. The liquids, they're not a solid anymore. They've melted, but they haven't yet turned into a gas. And then you get up to these solids and they haven't even bypassed their melting point yet. So these big molecules have very strong intermolecular forces, even though they're just dispersion forces. That's like a common misconception, is that dispersion forces must be totally weak. They are if you're comparing similar size molecules. If you compare water and a molecule that's similar in size to water, that's dispersion forces, then yes, of course the water is going to win. But if you compare a really large molecule that has dispersion forces to a small molecule that's hydrogen bonding, that's not really a fair comparison, and very likely the dispersion forces will win out. Okay, let's jump to a different group. So I always want to give you guys a minute to just like orient yourself here. So check out these three molecules, see what you can identify as far as maybe like what the dominant intermolecular force is, how they differ from each other. Take note of their boiling point. Okay, so all of these molecules have OH groups, those alcohol groups. So they're all hydrogen bonding. And the size does change, so like that could be playing into it. You get bigger molecules over here. So maybe it's not a completely fair comparison because there could be some stronger dispersion forces in glycerin. But since they're all hydrogen bonding, let's look at how they differ, not by mass, but by any other property, because it's going to be slightly different in hydrogen bonding. So the ethylene glycol, this is antifreeze, like the bright, crazy bright yellow-green stuff they stick in your car. Super toxic, by the way. There have been like multiple incidents. It looks like the lemon lime Gatorade. That is the color of it. And there actually have been like kids who have died because they drank it thinking it was a drink. It's really sad. Anyway, very poisonous. So that's got 2 OH groups on it. Glycerin, which is, you know how hand sanitizer is thicker? Like it's not just, it's rubbing alcohol basically with glycerin in it. So that's why it's a little bit thick and like gel-like. So that's glycerin, and that's got 3 OH groups on it. So comparing ethanol, which is just like straight liquid, ethylene glycol is like a little bit thicker, and then glycerin is very, very thick. And then if you look at their boiling points, glycerin has that really high boiling point, ethanol's is relatively low. So the key factor here, although the mass may have something to do with it, is the number of sites where you have that hydrogen bonding going on. So you've got 3 different places in glycerin where you've got an O bonded to an H. So I call those sites like more places where another molecule could come in and interact with it. So more H bonding sites is going to increase the strength of those forces. Remember, I'm just observing that because I see the higher boiling point. When I see the higher boiling point, I know that there's stronger intermolecular forces. So we're going to be like halfway through this by the end of today, the chapter. They always go fast. The first one feels like slow, the first unit. It's like, when are we going to have a test? And then all of a sudden, it's just like we churn through them. So we'll be halfway through 12 today. I would definitely take some time to do homework problems over the weekend, just so that you start to see, like, it's very concept-based, but at the same time, it's going to be pretty obvious once you do the homework, the types of questions they can ask you. So, like, the very basic would be, you know, here's two compounds and here's their boiling points. Which has the stronger intermolecular forces? So even if you don't know anything about the molecule itself, if you know its boiling point, you have an idea, or if you can compare its boiling point, you have an idea about the relative strength of those forces that are holding them together, because you have to break them in order to boil it. Yeah?
So is the takeaway from this that ethanol is the weaker intermolecular forces and glycerin is the strongest?
Yes, and the reason why is because ethanol has the smaller number of those OH groups in it. Yeah. So another example, if we look up at where we did those biological molecules up here, like you can see those biological molecules have tons of hydrogen bonding sites. So let's see, is this the only... Yeah, the two amino acids up here that have nitrogen in them. So they have those nitrogen-hydrogen bonds. The ATP has both oxygen-hydrogen bonds as well as nitrogen-hydrogen. The glucose is a great example because glucose is a solid at room temperature. That's because it has all of those OH bonding sites where it can form intermolecular forces. Okay? So the more of those you have, the stronger the forces are going to be between molecules. Okay, and then this last one is just a little bit of a note because we've seen, even in the first semester chemistry, we saw a decent amount of times where we dissolved salt into water. So we would not actually consider those an intermolecular force, right? But the water does have to be broken apart in order to let the ion come in. And then remember, the ion gets surrounded by the water molecules, either pointing into the negative with their hydrogens or vice versa with the positive. And those do create a force as well. So remember, when we talk about the strength of the intermolecular forces, it is completely dependent on how big those charges are. So if you've got a small partial positive and a small partial negative, the way you do with most dispersion forces, that's going to be relatively weak. If you have a relatively large partial positive and partial negative, the way you do with water, those are going to be a little stronger. Well, when you start to throw in ions, like from a salt, from an ionic compound, now you've got a relatively large partial positive from the water with a full negative from the chlorine. So these actually, not a highlighter, these actually create a pretty strong force between the ion and the water itself. So we call these ion dipole interactions. And they're relatively strong, like stronger than just a regular old hydrogen bonding would be. Which is why they'll actually dissolve. This is why salt will actually dissolve, because even though you have to break apart the water to get the salt to fit in there, that interaction between the salt and the water is really favorable. It's a very strong interaction. Okay. So, what we're going to do for the rest of today is talk about a few different properties of liquids specifically that also are affected by intermolecular forces. So, what I think we'll actually do, if you scroll down a few, to this chart here, let's start by having you guys just sort these molecules and predict their boiling points or melting points based on the intermolecular forces. So it'll be good practice. And then what we'll do is see how that correlates to these other properties: surface tension, viscosity, rates of evaporation. Okay, so I want you to take these 4 molecules. I feel like I should have given you the structure for this one, so I'm going to go ahead and do that. This one on the end looks like this. Okay. So basically order them from lowest melting point or boiling point to highest. Okay, maybe just another minute or so, and then we'll talk through this. Okay, so 2 of them are dispersion forces, so let's leave that for a minute. 1 is hydrogen bonding, so that's probably our strongest. So C2H5OH. And then this dipole one, that's probably the one in the middle. And then the 2 dispersion ones. So did anybody happen to add up the molar masses of these? No? Okay, that's okay. That's what you should do if you're trying to compare within a group. You should compare their molar masses. I know carbon dioxide's 44.01. I think C3H8, let's just do it real quick. Oh, where did my, there it is. Okay, so 12.01 times 3 plus 1.008 times 8. 44.1. Okay, so very close. So we can't actually tell the difference between those. So we're just going to put them together and say C3H8 slash CO2. Okay? All right, so that's just melting point and boiling point. We would expect those that to be the order from weakest or lowest melting point and boiling point up to strongest intermolecular force or highest boiling point. Okay? So these other properties, when we talk through these, you're going to need to know like what it actually means when we talk about surface tension, like what is that property, and then also how does that property correlate to intermolecular forces. Okay? I don't know why, but like these properties are hard to explain in words, I feel like. So I'm going to use my hands a lot, so just fair warning. All right, so surface tension. They've got this picture of a paperclip floating on water. This is like classic middle school science experiment, I feel like, where you see if you can float stuff on water. So the reason why that works is because when you think of the surface of water or any liquid, those molecules are being held together by intermolecular forces because that's what holds molecules together, okay? And if you want to break that surface, you have to push through those molecules and actually break them apart, okay? So the stronger that interaction is, the harder it's going to be to push through it. Think of like something solid, like, I don't know why I'm having a hard time thinking of something solid. I want a compound that's like just a single molecule. So like we talked about asphalt before, okay? So asphalt is roughly enough we could have a single molecule. Okay, well, can you push through and break those apart? No, those forces are very, very strong. Or ice. Can you push through ice just with your finger? No, you could set something on top, whatever. The thing is, some liquids can withstand a certain amount of force because their interactions are really, really strong. So water has relatively high surface tension. There's like insects and bugs that can actually walk on water because they don't apply too much of a force and they don't break that intermolecular force, okay? But there are certainly other molecules that don't have that kind of strength and that wouldn't be able to support any kind of weight, really. Okay? So that means that, I think this is down here, that the stronger those forces are, the more force it's going to be able to hold on top of it, and we would label that as having higher surface tension. So we can go back to our chart and say, okay, high surface tension also means strong intermolecular forces and therefore means each of these same molecules. So the trend is the same. So I'll just write same as above. In that the molecule with hydrogen bonding has stronger forces and therefore will have higher surface tension. Okay, viscosity is basically thickness, how thick something is. So if you think of honey and like trying to pour honey, it is very thick compared to pouring water. We would say, like a scientific way of saying that is it's viscous. This definition in words I actually think is pretty helpful. So the resistance of a liquid to flow. So think of a liquid in a container where it's in, basically as small of a surface area as it could be, okay? It's like in a ball shape, whatever, the shape of the container, a cup shape, okay? So all of those molecules are attracted to a bunch of other molecules around it. If you picture one in the middle, it's attracted to all of the molecules that are neighboring it. Okay, so there's lots of intermolecular forces when you have a big amount all in one space versus when you try to pour something and it flows into a stream, right? So if something has to be in a long, skinny stream in order to pour, that means that you're going from lots and lots of intermolecular forces here to breaking those up into very few intermolecular forces when you're pouring it. So the process, it's very odd because this is a physical process. We're not warming it up. We're not adding any energy that way. We're actually adding energy through a physical process of trying to separate those molecules into a thin stream. So the process of pouring involves breaking those intermolecular forces. And the stronger they are, like think honey or trying to think of another example. I don't want to use that. I don't know. I was thinking like corn syrup or something. Some kind of sticky, thick liquid that's going to be a lot more difficult for you to pour that, okay? You're going to have to break apart those intermolecular forces. So again, same thing as the one above. The stronger those forces are, the more resistant it's going to be to moving or to pouring. To flowing is the official way you would say that. So same as above. Really exciting. I always like the example of nail polish remover. So anybody who's ever used nail polish remover, obviously if you're painting your nails, but also nail polish remover is really good. Like everybody should have a bottle of it at their house because it's really good for getting out a lot of different types of stains, not necessarily on clothing, but like on surfaces, particularly plastic. So like if you get Sharpie on something, put some nail polish remover on it, it's going to come off like immediately. I have put it on my kids' faces before when they have like stuff that shouldn't be on there. Probably not the best idea. It's a little harsh on the skin, but whatever. Okay, so nail polish remover looks like this. Oh, I missed a carbon. CH3 on the sides. Okay, it's called acetone. So it's dipole-dipole forces versus water, which is hydrogen bonding. And if you've ever poured, I had a professor once that used to say the mark of a good chemist is their ability to pour things without spilling, because you like judge the viscosity of it based on, you know, the properties, you know, about the molecule. So if you try pouring acetone versus pouring water, they behave very differently. Like acetone is much more prone to like you splashing it or spilling it because it is way less viscous and it will pour really, really rapidly. The other thing that if you've ever used it, you'll notice is that it evaporates really quickly. So like if you get some, I mean, if you're just using it on your nails, it's not like water where you have to like go dry your hand. It's going to evaporate really quickly. Okay? So that gets us to our last one, which is vaporization. So vaporization is turning something into a gas, but not at its boiling point. It's evaporation is, you know, the common word we would use for it. So when something evaporates, not at its boiling point, all of it's going to evaporate pretty rapidly. Below its boiling point, though, assuming that it's exposed to the air, things are able to evaporate at a slow rate. Well, the stronger the intermolecular forces, the harder it is for those molecules to get enough energy to escape. So if you've got a container of water and a container of nail polish remover, you leave them overnight, the nail polish remover is probably going to be completely evaporated by the next morning. And the water, I would say, would probably take like a few days. Okay? That's because those forces in the acetone, the nail polish remover, are way weaker. And so those molecules can break apart from each other and turn into the gas phase a lot easier. So this one is actually opposite of the others. I don't even think I have it written down there. That the weaker intermolecular forces will have higher rates of vaporization. Or evaporation, if that's easiest for you to think about. So in each of these, you need to think like, what is the property? What is it that has to happen? Does it have to, like, what part of it has to break forces? And then you identify which one has stronger or weaker forces. So questions on these ones might be like, you know, here's two substances, which is going to be more viscous. Or here's two substances, and here are their surface tension values. You know, indicate why this one has a higher surface tension. Stuff like that. Okay, so I don't have the vaporization one in the chart. It's pretty closely related to this phase change thing, but we're gonna save that for next class because we're gonna do a lot of in-depth stuff with actual like calculations. So calculations for energy changes that are like the energy associated with breaking the intermolecular forces, like actual numbers and everything. So we'll do that in the next class. So kind of just wrapping up, making sure we're good with like categorizing the forces and everything. Let's just finish with this last practice set of molecules. And I want you to, again, indicate the dominant intermolecular force in each of these. Okay? So you may have to draw Lewis structures, maybe not. We'll see. I'm going to skip the last one. It's interesting, but I don't think we really have time for it, so. Okay, so I'll go ahead and label these, and you can check them as you finish. The last one, the reason why it's interesting, but I X'd it out, was because it depends on how you draw it, and not just draw it, but how it actually is. So it is also one that has an isomer, that one of them is polar and one of them is non-polar. Okay, so like I said, try to get some practice in over the weekend just so you don't feel slammed by it, you know, when the homework is due. I think it's like Thursday of next week. And it'll also probably make you feel more comfortable. The concepts always feel hard until you do some problems, and then it's like, oh, this isn't so bad.